Hello everyone, Assalamu alaikum. Welcome to the final project presentation of EEE 6609 Deep Learning Project. I am Kaji Ahmed Akbar Munim and today I'll be giving the presentation on behalf of my teammates Aranya Shaha and Muhammad Enamul Atik. Our project title is Learning Using a Single Forward Class. We are presenting this work to Dr. Muhammad Ariful Haq, Professor at the Department of EEE, BUET. Here is our outline of what we will cover in today's presentation. Problem statement, methodology, training MLP using Spela, training CNN using Spela, overall result comparison, and reference paper. Let's begin by addressing the core problem that motivated our project. As you can see in this simplified diagram, a neural network processes input through various layers to produce an output, which is then compared against a ground truth via loss function. The error from this loss is then propagated backwards through the network to update weights, and this process is called backpropagation. There are several limitations of this traditional backpropagation. First of all, it requires high memory uses because it needs to store all the activation functions, activation vectors during the forward pass so that they can be used for gradient calculation in the backward pass. And besides, we can train all layers in parallel because training a particular layer requires gradient calculated from the previous layers. These issues make traditional backpropagation approach unsuitable for edge devices or resource-constrained environments. To tackle these challenges, we propose solo pass embedded learning algorithm, or in short SPELA. It does not use any backpropagation, rather it updates the weights during the forward pass using local loss function. It uses symmetric vectors as ground truth at each layer. Looking at the diagram, you can see that each hidden layer works independently, which eliminates the need for a global error signal. Also, we can do classification at each layer instead of the final layer, which gives us early exit feature. Normally, the deeper layers produce more accuracy than earlier layers. In traditional neural networks, only the final layer typically has the ground truth. Hidden layers don't have direct ground truth and learn implicitly by backpropagation. But SPLS innovation is to provide a ground truth for every layer. This is achieved through what we call a symmetric vector. The main challenge was how to generate these layer-specific ground truths or symmetric vectors. We found our inspiration in nature, specifically from electrons' position in an atom. In order to achieve the lowest potential energy state, electrons tend to maximize their distance within an atom from each other due to repulsion. Inspired by this model, we created some symmetric vectors with a dimension equal to the number of neurons in a layer, ensuring that they are equidistant from each other in high dimensional space. And each symmetric vector now represents a particular class, and we will train the model to align the input vectors with its corresponding symmetric vector through cosine similarity loss function. We have used M.Sc 10 dataset for training MLP. M.Sc dataset contains handwritten digit images from 0 to 9. The images are in 28 by 28 pixel grayscale format. It has 60,000 training images and 10,000 test images. Here we present the learning curves of our two-layer MLP trained model with Spela. On the left, we have the training loss per layer. Here, layer 2 shows more rapid decrease in loss than layer 1. We can see that the training accuracy per layer graphs on the middle and the test accuracy per layer graphs on the right. Both layers quickly converts to high accuracy levels during training and shows good performance on unseen data during testing. Layer 2 shows better performance than layer 1. And let's look at the final results. We have achieved test accuracy of 92.015% at layer 1 and 92.84% at layer 2. The dimensions of layer 1 and 2 are 128 and 10 respectively. This slide provides a closer look into the learned parameters of our SPLA trained MLP. On the left, we can see the distribution of weights and bias in each layer, and on the right, we can visualize the symmetric vectors for each layer from the heat map. We have used Cypher10 dataset for training CNN. This contains 32 by 32 pixel RGB images among 10 classes. It has 50,000 training images and 10,000 test images. Before discussing SPLA CNN framework, we can look at how traditional CNN work. In a normal CNN, typical CNN, input images are passed through a series of convolutional layers which extract feature maps using various kernels. These feature maps are flattened and then entered into fully connected layer for classification. During the training, the error from this final output is backpropagated through all the layers to adjust the weights and bias. And This process is memory and computationally intensive, and it becomes more so with deeper CNN layers. Now let's look at our Spela framework for CNNs. It retains the core principle of local learning. Input images first passes through a convolution operation to extract initial feature like feature 1. This feature 1 is then fed into an MLP like MLP1, which performs classification based on its local symmetric vector. This entire block is followed by a local loss function. And this process can be extended by layers. The first feature map or feature 1 can also be used as the input for the subsequent layers, subsequent kernels like kernel 2 to extract feature 2, which is then passed to an MLP2 for its own local classification. And each stage can act as independent learning module. Here we present the learning curves of our two-layer CNN model trained with Spela on the Cypher 10 dataset. The training loads per layer graph on the left shows a clear reduction in loss for both layers, while loss for layer 2 decreases more rapidly. And the graph on the right provides a combined view of training and test accuracy per layer. The accuracy values are lower than those achieved with MLPs on MNIST dataset because Cypher 10 is more challenging dataset than MNIST. We have achieved a testing that accuracy of 41.43% at layer 1 and 55.35% at layer 2. These slides provides an overall comparison of our Spela implementation against the results reported in the reference paper for both MLP and CNN. The reference paper used a two-layer MLP with a dimension of 1024 and 10, while we have used 128 and 10. Both used positive cosine as the loss function. For layer 1, the reference paper's Spela MLP achieved 91.18% accuracy, while our Spela MLP model achieved 92.05% accuracy, showing a slight improvement. At layer 2, reference paper Spela MLP got 94.49% accuracy, and our Spela MLP achieved 92.84% accuracy. And the highest accuracy on MNIST 10 dataset by using backpropagation MLP is 98.56%. As for layer, as for CNN, its input size was 32 by 32 by 3 with 32 kernels per layer and a kernel size 5 and stride 1. It used positive cosine loss function. For layer 1, Spela CNN from the reference paper achieved 44.35% accuracy, while our model achieved 41.43%. At layer 2, Spela CNN in the reference paper got 56.59%, and our Spela CNN achieved 55.35%. And the highest accuracy on Cypher 10 dataset by using backpropagation CNN is 64.99%. Our project is based on the research presented in the paper titled Learning Using a Single Forward Pass, which was published in Transactions on Machine Learning Research in June 2025. We have carefully implemented the model by coding it ourselves based on the algorithm and ideas presented in the paper. This concludes our presentation. Thank you, everyone.